Chapter 5, Neural Interfaces, Bridging the Brain-Machine Divide. Neural interfaces represent a revolutionary field at the intersection of neuroscience, engineering, nanoelectronics, and computer science. These interfaces facilitate direct communication between the brain or nervous system and external devices, enabling control of prosthetic limbs, restoration of sensory functions, and treatment of neurological disorders. This chapter explores the principles, development, current applications, and future prospects of neural interfaces, focusing on their transformative impact on bridging the brain machine divide. Imagine being able to control a computer or a prosthetic limb just by thinking about it. Welcome to the world of neural interfaces, a field where nanoelectronics meets neuroscience to create a seamless connection between human brain and external devices. These interfaces translate neural signals into commands that control external devices or stimulate neural tissues. Neural interfaces, also known as brain-machine interfaces or BMIs, have the potential to transform the lives of individuals with neurological disorders, spinal cord injuries, and limb amputations. By decoding neural signals and translating them into commands, these interfaces can restore lost functions and enable new ways of interacting with the world. At the core of neural interfaces are arrays of tiny electrodes that can record electrical activity from neurons. These electrodes, often made from advanced materials like silicon or carbon nanotubes, are designed to be biocompatible and minimize tissue damage. The recorded signal are then processed by sophisticated algorithms and decode the neural activity and converted into actionable commands. The integration of nanotechnology and advanced signal processing has significantly enhanced the capabilities and applications of neural interfaces, making them a transformative technology in healthcare and beyond. Neural interfaces can be classified based on their invasiveness and application. Invasive interfaces include microelectrode arrays implanted into the brain or nervous system. And non-invasive interfaces uses EEG, fMRI, that is functional magnetic resonance imaging, or NIRS, that is near infrared spectroscopy, to detect neural activity from outside the body. Also, hybrid interfaces combines invasive and non-invasive approaches to achieve higher resolution and functionality. One of the most well-known applications of neural interfaces is in the control of prosthetic limbs. Imagine an amputee being able to move a robotic arm just by thinking about the desired movement. This is not science fiction. It's a reality made possible by neural interfaces. By implanting electrode arrays in the motor cortex, the part of the brain responsible for the movement, researchers can capture the neural signals associated with specific motions and use them to control prosthetic devices. Neural interfaces are also making strides in restoring communication for individuals with severe disabilities. For example, patients with locked-in syndrome, who are unable to move or speak, can use neural interfaces to communicate through computer systems. By decoding the neural signals associated with intended speech or movement, these interfaces enable patients to control a cursor on a screen, type messages, or even speak through a synthesized voice. The potential of neural interfaces extends to the realm of cognitive enhancement as well. Researchers are exploring ways to use these interfaces to augment memory, learning, and other cognitive functions. Imagine a future where individuals can enhance their cognitive abilities or recover lost functions through brain-machine connections. However, developing neural interfaces is a complex and challenging endeavor. ensuring long-term stability and biocompatibility of implanted electrodes, achieving high signal-to-noise ratios, and creating effective decoding algorithms are significant hurdles. Nanotechnology plays a crucial role in the development of neural interfaces by improving electrode performance and biocompatibility. Nanomaterials such as carbon nanotubes, graphene, and conductive polymers are used to enhance electrode conductivity, reduce impedance, and improve longevity of neural interfaces. Also, advanced signal processing techniques and machine learning algorithms are essential for decoding neural signals and translating them into meaningful commands. These techniques enable real-time control of prosthetic devices, adjustment of therapeutic parameters, and prediction of patient intentions. Advances in material science, signal processing, and machine learning are driving this field forward. Innovations such as flexible electronics, wireless communication, and minimally invasive implantation techniques are making neural interfaces more practical and accessible. Recent advances in neural interfaces encompass several groundbreaking technologies. High-density electrode arrays, equipped with hundreds to thousands of electrodes, enable precise mapping and stimulation of neural circuits. Closed-loop systems represent another significant development. These systems monitor neural activity and adjust stimulation parameters in real time, responding dynamically to changes. Optogenetics, a technique involving light-sensitive proteins, allows for modulation of neural activity with exceptional spatial and temporal resolution. Additionally, implantable devices with wireless communication capabilities are emerging, facilitating both data transmission and power delivery without the need for physical connections. These innovations collectively enhance the functionality and versatility of neural interfaces, paving the way for more sophisticated and responsive neurotechnological applications. Challenges in the development and deployment of neural interfaces encompass several critical areas. One significant challenge is biocompatibility, which involves ensuring that materials and devices do not provoke immune responses or tissue rejection. Another major challenge is maintaining long-term stability, as it is crucial for devices to perform consistently and remain functional over extended periods within the body. Additionally, managing large volumes of neural data for real-time processing and communication presents a substantial data bandwidth challenge. Ethical and privacy concerns also play a pivotal role, as the deployment of invasive technologies requires careful consideration of their ethical implications and robust measures to protect patient privacy. Looking ahead, future research directions for neural interfaces are focused on several key areas. Miniaturization and integration are vital for developing smaller and more integrated devices that can be implanted with minimal invasiveness. Advances in biocompatible materials and coatings aim to improve biocompatibility and reduce immune responses. There is also a strong emphasis on enhancing closed-loop systems to provide adaptive and responsive therapies. Moreover, the concept of brain-cloud interfaces is emerging, which involves connecting neural interfaces to cloud-based platforms for comprehensive data analysis and sharing. These directions highlight the ongoing efforts to overcome current challenges and advance the field of neural interfaces. In conclusion, neural interfaces represent a transformative technology that is bridging the gap between brain and machines, enabling precise control, sensory restoration, and therapeutic benefits for individuals with neurological disorders and injuries. By leveraging nanotechnology, advanced signal processing, and machine learning, researchers can develop sophisticated neural interfaces with broad application in healthcare, research, and cognitive enhancement. While challenges remain, the future of neural interfaces looks promising, with continued advancements expected to improve patient outcomes, enhance quality of life, and deepen our understanding of the brain. Thank you.